Hello, IB Environmental students. Today we're going to be talking about, you're going to want to draw a simple version of this as best as you can. We call this a sankey diagram, spelled S-A-N-K-E-Y, sankey. What is a sankey diagram? Well, it shows us how matter or energy is moving or flowing through an environment by showing us the amounts through the widths of the arrows. The Earth's energy budget is shown through this sankey diagram, and it allows us to see the percentages through the widths of the arrows in addition to having the percentages drawn. So we have the total amount of original energy coming in, solar or light energy. Now we can then see what happens to the light energy that is always shown here in yellow. A lot of it gets reflected through different ways, the atmosphere, the clouds, or off the Earth's surface. But some of it gets transformed or converted into thermal or heat energy, which is shown here in red. Remember that when you're sitting on blacktop or dark pavement, that dark pavement's going to feel warm compared to, for instance, something like ice, which is just going to reflect off the light like a mirror. So that warming or heat, that's this red, all right? Sometimes we call that re-radiating. That's the heat radiating heat, all right? So what I would do is pause and try to draw this in your notes. I'm going to then highlight some key examples of some of these pathways in the next slide that you can write out in short sentence form. So some of those pathways we saw on the previous slide that hopefully you drew were that sunlight coming in with the big wide arrow of 100%. And then we saw that there was some loss reflecting back off of things like ice caps, which we discussed were like mirrors. We say that that has a high albedo or reflectivity. Other things that have a low reflectivity absorb a lot of energy, and those things are like soil or water. Between soil and water, which do you think absorbs more energy? Soil, because it's a lot darker. Water does some reflection, but it also can absorb the energy. When it's absorbed, we call it converting to heat energy or thermal energy. We know that changing from light energy to heat energy would be an example of a transformation. Then, because it's getting warm, that gets re-radiated back into the atmosphere. Some of that light energy gets converted or transformed into chemical energy through the process of photosynthesis, which is done by producers. Amazingly, only less than 0.1% of the light energy initially coming in gets used for photosynthesis. Whoa! Last, we know through our food web information and pyramid information we've learned earlier in this unit that not all the energy moves between trophic levels. In reality, only 10% of energy moves between trophic levels, and 90% gets lost as heat. So that's called our 10% rule, which we remember from the second law of thermodynamics. Let's keep going. Next, we're going to review some stuff from biology. We're going to review photosynthesis and cellular respiration. You don't need to know the chemical formulas, but you need to know the basics. We're going to talk about it as systems using inputs and outputs. Inputs, remember, are like our reactants: sunlight, carbon dioxide, and water. Carbon dioxide is in the atmosphere, and it's called inorganic carbon because it is not in a living organism, and it does not have hydrogen. To be organic, you have to have carbon and hydrogen, such as sugar, which is formally known as glucose, which if we look at sugar, it's a C and an H and an O, meaning it's an organic molecule. Sugar is the food energy that an autotroph or producer is making on its own. So what do we know from our systems? Did we convert something and transform it? Yes, we sure did. We transformed light energy into chemical energy, storing that energy from that inorganic carbon dioxide from the atmosphere into the organic form of carbon in the sugar. We do know that some organisms don't use light energy to do this process. They use chemical energy, and a lot of those organisms live in the deep ocean where there's not a lot of light. We don't normally talk about those chemosynthetic organisms a lot, so don't worry about them too much. Next, there's cellular respiration, which is the opposite process of photosynthesis. Just know that all living things do cellular respiration, not only animals, but plants too. So the inputs for this process are those food energy molecules, sugar and oxygen, and the outputs are usable energy, ATP, which you don't need to remember too much in this class, carbon dioxide and water. Remember, these are the opposites that were in the photosynthesis equation. But what's the really big part that we need to know? Well, we need to know the transformations in this process. That in this process, we're taking the chemical energy in sugar and we're changing it to usable energy. And through that process, we're creating heat. All right? And that's going to be related to entropy, which we've talked about before in this class. Our respirational loss as entropy is going to be thought of like a tax that's on a plant or on an animal. Because every time we're living or respiring, we are taking a little bit of energy and a little bit of matter out of our system. So to talk about this, so related to this is this idea of productivity. We have a couple different terms about this depending on if we're a plant or an animal. So if we're a plant, we're going to call it primary productivity. First, there's gross primary productivity, which is the basic amount of light energy that's going to be converted into chemical energy or matter by photosynthesis. Think about this as how much a tree grows. All right? How much is the tree or the plant growing? If I were to weigh it, how much did it grow in a specific area in a specific time? Which is pretty interesting. All right? It tells me how healthy or how much rain or light is available in that area. But then I have this thing that's the after taxes, the net, which is usually smaller. Remember, respiration is like the taxes for a plant or an animal, and it's going to be related to that heat or entropy loss. So after respiration, and I account for that the plant is doing all the activities it needs to do to survive, it's going to lose some energy and biomass. If I'm asking for net primary production, I'm accounting for those losses of respiration. Let's do a practice calculation. All right, the GPP of producers in an area, which is a large rainforest, is 0.00 grams per centimeter squared per day. All right, so they have a little quadrant that they're measuring, and they measured the biomass, which is the dry weight. And they know that 25% of this productivity was consumed in cellular respiration. That's just something that they know from this word problem. That's not always the case. Then the problem asks for us to calculate the NPP. To do a word problem, we always want to see what is the information we know. Well, we're looking for NPP. What other things do we know? Well, it gives us the GPP. It says that amount. And then, does it give us the information about respiration? Because we need to know respiration in order to calculate NPP, which is after taxes, or after respiration, which is like our taxes. Well, it says that respiration is 25% of the GPP. So I can take this number and times it by 0.25. And that gives me the respiration based on my word problem. So now I can look up, okay, what was that equation again for NPP? Oh yeah, it was the GPP minus the respiration or taxes on the plant. And that was the equation that we need to use. So now I have all my information to plug it into my equation in order to calculate NPP. So here's what I would calculate. Notice that I have an extra significant digit here, so I would want to round. Right? I would want to put 0.0038. Good job. All right, let's move on. So far we've talked about plants. What about animals? Well, animals are a little bit more complicated because they do things like poop and pee. So now we're going to call it, instead of primary, we call it secondary productivity. And secondary productivity, since it's an animal, is going to involve what the animal's eating. And it might eat a plant or it might eat an animal. So we call what it's eating the energy or biomass that it assimilates. What it ate, assimilating it, eating it. But then we're going to have to account for, guess what? Plants don't poop or pee, but animals do. So we're calling poop fecal losses, sometimes called feces, right? So now we're going to think about this bunny ate that plant. Nom, 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 nom. But then it also poops. So we have to account for that it pooped, okay? So we would measure what it ate minus what it pooped out, and that would give us our productivity. Now this is a little hard because normally when we do biomass, we want to do dry biomass, and we wouldn't want to kill the bunny. So doing secondary productivity actually outdoors and in the lab is really hard. So that's our equation so far. Okay, but what about the net secondary productivity? Well, remember, net refers to after taxes, and in our calculations, what represented taxes? Respiration. So now for net secondary productivity, I have what? This guy, same pattern, minus our respiration. So what are the daily activities that bunny's doing that might cause it to heat up or respire? So now I'm going to subtract the R. So we could get the same exact data that we got in other calculations. We would just need extra information called fecal losses. And it would be just as possible to calculate this. Notice that there's that same pattern. We have gross and net always is subtracting respiration. All right, now let's see what this looks like in some graphical forms. So we would use this information to understand the differences between different biomes, which is somewhere we're going in this class. Remember, productivity tells us how much growth there is, whether it's an animal or a plant. Now this up top says net primary productivity. Is that plants or animals? Primary, plants. So here we're talking about what is the plant growth over time in different biomes. So which ones look most productive? Estuaries, like our Chesapeake Bay. Rainforests, and temperate, like where we live. Well, this makes sense that rainforests and marshes and estuaries, like the Chesapeake Bay, have the most plant production. Why? Because they have the best abiotic factors. All right, what kind of abiotic factors make a tropical rainforest more productive? The light, the temperature, all right, the rain. Versus a place like the desert, is there a good amount of rain? No. So are the plants growing a lot? No. So we can use this information to make good data-based decisions on why different biomes are more or less healthy. And we would now call healthy primary productivity when we're talking about plants. We're going to practice this more in class. We can also construct and analyze energy flow diagrams. This is the same idea when we were talking about systems earlier in the year, where boxes are storages, all right? Usually the boxes are going to be the different trophic levels. So here we have a producer, we have herbivores, which are our primary consumers, and then we have secondary consumers. We can have labels that have information about the amount of energy that's flowing on the arrows, and we can use that to try to calculate different things. All right, so we also can use what we saw in our energy budget sankey drawing to draw arrows that have different widths. So sometimes the arrow width is representative of the amount. So notice that this 10,000 is much wider than that 700. And please don't try to draw that. That's way too complicated. So big idea, we can use this information to analyze graphics. We're going to practice that in class because it's too much to draw here. But the big idea is we are now seeing storages and flows and transformations of energy. And we can use that information to talk about the health of an ecosystem, the productivity of an ecosystem. Very cool. Good job.